In this tutorial, we will discuss the fundamental concepts of the Brayton and Rankine thermodynamic cycles. These two cycles provide the basis for which gas turbines and steam turbines operate. Knowledge of these cycles will help us understand how turbines operate and how their performance is evaluated. We are interested in the amount of energy required to produce some product. As the efficiency of our process increases, we are able to produce a larger quantity of a product with the same amount of energy, or, for a given quantity of output, less energy is required. Before we evaluate the performance of these cycles, we will first introduce some important definitions and the properties that are used to determine efficiencies. A thermodynamic system is a quantity of matter or a volume in space chosen for study. Thermodynamic systems can either be open or closed. A closed system has a fixed mass, and mass cannot cross the system boundary. Open systems, such as a compressor, turbine, pump, or boiler, involve mass flow. The state of the system is described by its thermodynamic properties. If we know any two independent intensive properties, we can determine the state. Intensive properties are those which are independent of a system's size. Usually temperature and pressure are the easiest to obtain. For our purposes, we will use these intensive properties to determine enthalpy or entropy at different state points in the cycle. Enthalpy is a property that represents the amount of useful energy that is stored in the working substance. Enthalpy has two parts, the internal energy and the flow energy. Entropy is a measure of the irrecoverable work which is lost from the system between the energy input and the energy output. These irrecoverable losses include heat transfer between the system and the surroundings, as well as irreversibilities. Irreversibilities include factors such as friction and vibration. When these losses occur within the system boundary, they are called internal irreversibilities. These two factors, internal irreversibilities and heat transfer, change the entropy of the system. In the real world, all these losses can be minimized, but they cannot be eliminated. Processes follow a certain path between their initial and ending states. We can view this path on a temperature entropy or TS diagram. In an isentropic process, the system's entropy remains constant. In other words, this ideal process is internally reversible, and there is no heat transfer between the system and its surroundings. The internally reversible process follows the same path when the process is reversed back to the initial state. When we study the efficiency of the Brayton and Rankine cycles, we will be comparing the work done by the actual process to the work done by the system if it were to operate isentropically. In simple terms, all the input energy is converted to useful work in the isentropic process because there are no energy losses. The sign convention that will be used for heat transfer and work will go as follows. Heat entering the system is positive. The heat that is transferred from the system to the surroundings is negative. Work is just the opposite. Work is energy that crosses the system boundary that is not in the form of heat. Work done on a system is negative, and work done by a system is positive. A brief introduction of the first law of thermodynamics is in order before we begin to analyze the Brayton and Rankine cycles. The first law of thermodynamics, or the conservation of energy principle for the steady flow devices, is shown by this equation. This principle explains that energy is never created or destroyed. It simply changes in form. In our analysis, we will neglect the kinetic and potential energies of the working fluid as it flows through the control volume. Kinetic energy involves the velocity of the working fluid. As long as the inlet and exit velocities do not vary too much, the change in kinetic energy is small. Similarly, the change in potential energy due to elevation differences is very small, especially in turbines and compressors. The potential energy would be a factor in a process where fluid is being pumped to high elevations. The enthalpy values at the inlet and exit states of the process can be found in the steam table. Any thermodynamics reference book should contain steam tables for water. The ideal gas properties of air and other gases, such as methane and hydrogen, are readily available in reference text as well. To determine the enthalpy at a state, you must first know two independent intensive properties as we discussed earlier. The properties most commonly used are temperature and pressure. If the phase and pressure of a substance remains constant during a process, then the change in enthalpy is also equal to the specific heat multiplied by the change in temperature. The specific heat is defined as the energy required to raise the temperature of a unit mass of a substance by 1 degree. There are two kinds of specific heats. The specific heat at constant pressure, denoted here by C sub P, and the specific heat at constant volume, C sub V. Specific heats remain relatively constant over a given temperature range, but vary widely for different substances. For example, C sub P for air is 0.240 BTUs per pound degree Fahrenheit. For water, C sub P is 1 BTU per pound degree Fahrenheit. Click on either thermodynamic cycle to learn about the efficiency of that cycle in detail.